All right, today we're going to jump into chapter 2 of our book, which is going to be our second big unit. And we're going to begin talking about something called a derivative. And specifically, we're going to talk about the limit definition of a derivative today. So we're going to kind of link the previous unit, which we talked about limits, to our next unit, which is a very, very important part of calculus on derivatives. And in this little cartoon here, this is actually the definition we're going to be talking about here. It's a bit complicated, but we'll sort it all out. So as we talk about something called differential calculus, that differential comes from derivative. So there's differential calculus and there's integral calculus. This unit will focus on differential calculus. We're basically trying to try to solve one basic problem. This is a problem that back when calculus was first sort of invented by Newton and Gottfried Leibniz, they were basically trying to solve this one problem. That problem is, what is the instantaneous rate of change of some given object at a given point in time? So prior to this, they had methods for finding the average rate of change, right? That's easy enough to calculate. An average rate of change is just a slope. That's something that you've called slope from, back in 7th grade or whatever, an average rate of change. But we don't have a good way of finding an instantaneous rate of change. So for instance, we can calculate, how fast a runner is going, an average rate of speed, from if they're running a 100-meter dash and it takes 10 seconds to do so, then we can calculate, well, they went 100 meters and 10 seconds. So you can calculate the average speed in that way. Same with the car, right? If it takes you 2 hours to travel someplace and you're driving 120 miles or whatever, you can figure out you're traveling 60 miles per hour. However, if we want to know the rate of speed of your car or a runner at a given point of time at an instant, we don't have a good way of figuring that out. So that's why we need derivatives. So let's first by taking a step back and looking at an average rate of change, and then we'll sort of link this to an instantaneous rate of change. So if we're asked to find an average rate of change, I've got a function here. And if we're looking to find the average rate of change, we're essentially looking to find the slope of a secant line. I mentioned this briefly a while ago in a video when I first introduced calculus. But a secant line, if you remember, if you use basically the idea of a circle, a secant line is a line that hits a circle in 2 places, whereas a tangent line hits in exactly 1 place. So we're going to talk about the difference between those two. All right, so for a secant line, let's say we're going to calculate the slope between the points 1, 1 here and the point 3, 10. Well, we have a good formula for using this, our slope formula, y2 minus y1 over x2 minus x1. Which another way of writing this in function notation would be f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. Would be another way of looking at that, right? So in this case, we would have f of x sub 2, that's our y coordinate, that would be 10, minus f of x sub 1, that'd be our y sub 1, so that'd be 1. And then our x sub 2 is 3, and then our x sub 1 is 1. So we've got this is x sub 1, this is f of x sub 1, this is x sub 2, and this is f of x sub 2. That's where I got those numbers. All right, and then we would just do 10 minus 1, which is 9, 3 minus 1, which is 2, so it would be 9 over 2. That would be the slope of the secant line between those 2 points. In other words, if I were to draw a straight line connecting these 2 points, I'm not going to be perfect, but like that, the slope of that line would be 9 over 2 or 4.5. Okay, now let's take this to our derivative, which is an instantaneous rate of change. So if we're looking for an instantaneous rate of change, And let's say we're not trying to find it between these 2 points, but let's say we're trying to find the instantaneous rate of change at a specific point at the point 1, 1. We want to know what is the slope of a tangent line that hits at exactly that 1 point. So an instantaneous rate of change is the same thing as finding the slope of a tangent line at a given point. So notice this point only hits the curve at exactly 1 point. It's not a perfect tangent line. My drawing's not, but you get the idea there. It only hits at 1 point. So it doesn't intersect at 2 points. So how could we calculate a slope if we only have 1 point? Well, the way that we're going to do that is actually using limits. So let's say we're going to approximate this by, if we sort of start out here at our second point at 3, 10, we were to draw a line that, right? But maybe we want to move a little bit closer, so we move it to here. We want a little bit closer, so we move it in here. And we want a little bit closer, so we move it here. And eventually we just keep moving the second point closer and closer till we get the slope of the tangent line. So what we're actually doing is we're taking the second point and we're sort of taking the limit as it gets closer and closer to this point 1, 1. Let me erase these out real quick and show you a little bit better what I'm talking about here. Oops, didn't work. Just erase it all. Okay. So what we're going to do, some notation we'll introduce here. So here's my point 1, 1. And my second point, which I'm going to keep moving. So I've got my first line, it's here. And then if I sort of move it down here and move it a little bit closer, the distance between the first one and the second one, I'm going to call h. Okay. So if my first point, again, we're just keeping it here at 1, 1. And my second point, it's kind of moving. All right, let's say I'm just going to put it here for now. If this point is, we'll call it x, f of x, right? In this case, it's 1. That's x, f of x. This second point, I'm going to refer to as x plus h, f of x plus h. Okay, and the h is the distance in the x direction from here to here. So this is the h from here to here. That distance is distance of h. So whatever the point is, I'm talking about here, if this is 1, 1, then the other point, their x sub 2, would actually be 1 plus h. Okay. And then if my first f of x was f of 1, well, then my next point would be f of 1 plus h. So then what's going to happen is this h, we want to keep making it smaller and smaller because we want to keep moving this h point here and here. So the distance here is h, right? So we keep making this h and h smaller. So in other words, we want the h, the distance between the first and the second, to be as small as possible. Ideally, we would like it to be 0. So we want h to be 0 or infinitely close to 0. And how we can do that is by taking the limit. So if we start with that definition from our previous slide there, our basic slope definition, if these are our coordinates here, x and f of x, and then x plus h and f of x plus h, what our slope formula changes from, if it was originally, we thought of it as f of x sub 2 minus f of x sub 1, right, over x sub 2 minus x sub 1. And we change those out for these points that we've defined here. Our slope then becomes, this is our f of x sub 2, right? So that's going to be f of x plus h. Our f of x sub 1 is just f of x down here, right? So it's minus f of x over, now our x sub 2 is this right here, x plus h. So x plus h minus, and our x sub 1 is just x, so minus x. So this is what we end up with. And if we just simplify this a bit, the top we can't really do anything with. It's f of x plus h. We can't combine that in any way. But the bottom, we got an x and a minus x, you can see. Those actually cancel out. So we're actually left with just h on the bottom. So this is a formula for essentially our slope of our tangent line. Now, in order to make this actually work, we want the h, the distance, in the x direction to be as small as possible. So what we do is we take the limit of this as h goes to 0, because we want to know what happens as this h, this distance between the 2 points, gets as close to 0 as possible. Well, the way that we figure out what's happening of behavior of a function as close to the point as possible without actually being that point, we take the limit of it. So we're going to take the limit of this formula, you can think of it, as h goes to 0. And again, h is the distance. You can think of it as between our x sub 1 and x sub 2. Think of it in that way. But we want h to be as small as possible because we want our x coordinates to be as close as possible. Ideally, we want it to be 0. So we're going to take the limit as h as that distance goes to 0. So essentially, there's no difference between these 2 points. We sort of want to eliminate the difference. This is kind of a hard concept to get. Hopefully you're getting it. It's even a little bit more challenging to teach it on the computer, but hopefully you're kind of understanding what's happening here. We're essentially trying to make the distance between, in other words, you want these 2 points that we're going to use to be as close to each other as possible, and essentially want it to be the same point. All right, so this is sort of our working definition here of the limit definition of a derivative. This is a derivative. An alternate notation that you might see, sometimes instead of seeing h, you'll see it referred to as delta x. That means the change in x. So you might also see this as limit as delta x goes to 0 of f of x plus delta x. I actually like that one a little bit better. It makes more sense to me. But the AP, I believe, uses the h, and your book does as well. But I've seen this delta x as well. Delta x just means the change in x. So as the change in x goes to 0, we find the limit as the change in x goes to 0 of f of x plus delta x minus f of x, sorry, that should be x, over delta x. Means the same thing. Sometimes you might even see a t or something instead of the h, but it all means the same thing. It's just saying the delta x or the h is sort of the distance between the first and the second x coordinates. And we want that distance to be as small as possible, ideally 0, so we take the limit as that distance goes to 0. All right. So here's our limit definition. This is the formula that I just wrote out. This is something that you do need to memorize. Practically speaking, we're not actually going to use this a whole lot after we get past this section, but the AP does expect you to know and be able to know how to use this definition. It turns out there's actually shorter ways to find the derivative. We're going to learn a bunch of shortcuts to do so, but this is the actual mathematical way that we're going to calculate a derivative. Notice the notation here. The way that you pronounce that is f prime of x. And that's what we're going to use the notation for a derivative. F prime of x equals the limit as h goes to 0 of f of x plus h minus f of x over h. And sorry, I can't see that so well. The sort of the wordy definition of a derivative, we said that the derivative of a function at a particular point is the slope of the tangent line to a graph of the function at that point. So the derivative at a point is the slope of the tangent line to a graph of the function at that point. I know that's kind of hard to make sense of that whole definition, but think of derivative sort of as two things. Derivative is the slope of a tangent line, and it's also an instantaneous rate of change. So if you can remember those two things, derivative is the slope of a tangent line, which also means it's an instantaneous rate of change. Those are sort of our two main applications and the two definitions of what a derivative is. Some other notation you'll see for derivatives. Get to work here. The first one I just wrote there was f prime of x is how we pronounce that. This is pronounced, whoops, what happened there? F prime of x is how we say that first one. The second one, we just generally call it y prime. That's how you pronounce that. Don't know what happened there. I might need to exit this real quick. Sorry here. Keep it. Try this again. So this is f prime of x. This is pronounced y prime. And the way we pronounce this is dy dx. You could say dy over dx, but generally I just say dy dx. Those are all different derivative notations. The y prime kind of makes sense because, as we've said in really algebra 2, pre-calculus, even algebra 1, we've kind of said that f of x and y are sort of synonymous, right? Y and f of x are. So f prime of x would be the same thing as saying y prime. The dy dx, the d kind of stands for change in. So it's kind of like the change in y over the change in x. That's sort of what it means, dy dx. All right, so let's go ahead and solve some problems. Now we've got a little bit of a foundation here. We're going to start by finding the derivative at a specific point, and then we'll talk about how to find the derivative in general, which we could then sort of just plug in at any given point that we want to. So to find the derivative at a given point, we're going to use the definition we just talked about, except I just made a slight change here. All I did was change out the x's for what we'll call an a. All right, a is just a constant. So this is, a is a constant. This is the exact same definition, except we just use a instead of x because we're finding it at a specific point. But again, it's exactly the same. This is how your book and AP refer to finding the derivative of a point. So, all right, let's go ahead and do it. So in this case, and in our example, we're finding the derivative at x equals 1. So this is our a equals 1. So when we compute this derivative, we're going to say f prime of 1 equals the limit as h goes to 0 of f of 1 plus h minus f of 1, because remember a is 1, over h. And we've got to figure out how to solve this. Okay. Well, we're first going to start by replacing the f of things with what the actual function is, which is 2x plus 1. So this is going to become, now instead of f of x, we're replacing our x's with 1 plus h. So this gets replaced. So this is going to become 2 times 1 plus h squared plus 1. So that's our f of 1 plus h. That's what we've done so far. Minus, we'll do a parenthesis, f of 1. So f of 1 is 2 times 1 squared plus 1 over h. Technically, I should have that limit there as well. All right, if you need to pause it for a second and just sort of like get your bearings on what I actually did, all I did is replace the x with 1 plus h in the first function, and I subtracted, replaced the x with 1 on the second function. All right, so from here we need to solve this. Well, anytime you evaluate a limit, the first thing that you want to try to do is direct substitution. Direct substitution isn't going to work here because obviously we're going to get 0 in the denominator. So we need to do some simplifying in this. All right, so we end up with the limit as h goes to 0. Let's just simplify the top of it. 2 times, and then the 1 plus h squared, you have to FOIL that. When you FOIL that, you're going to get 1 plus 2h plus h squared plus 1. And then we do have to distribute that minus sign, but it will become minus 3, right? Because 1 squared is 1, 2 plus 1 is 3. All right. Over h. Okay, and we're just going to keep simplifying here until we get something that works. So the next one we'd have is limit as h goes to 0. Let's go ahead and distribute this 2 in. That becomes 2 plus 4h plus 2h squared plus 1 minus 3 over h. Switch colors here. All right, and you'll start to see some good things here, and that is we're going to get some cancellations. So we got the limit as h goes to 0. We've got 2 plus 1, which is 3, minus 3. So these constants all get canceled out. This should always happen when you do this. Should always happen, at least on these basic ones. Should always happen is the constants have to go away. And then what we're left with is 4h plus 2h squared over h. And hopefully you're seeing now that the top has only terms with h in them, which is what we want. We want to get all the constants out, because if we have an h in all of these terms, then we can factor out an h. So then our next step, limit as h goes to 0, we're going to pull out an h, so this becomes h times, and you can pull out a 2 if you want to as well, but it doesn't matter, h times 4 plus 2h over h, and then we get that cancellation that we're looking for. So the h and the h cancel. I'll finish this up over here, sorry. So then we're left with the limit as h goes to 0 of just 4 plus 2h, right? Because the bottom went away. And now we can direct substitute. So then our final step to plug it in is now just 4 plus 2 times 0. 2 times 0 is 0, so it's just 4. So what we've said is now what this means, right? This means that the slope of 2x squared plus 1 at x equals 1 is 4. That's what we've said. That's what we figured out. The slope of the tangent line at x equals 1, and this is the same function, by the way, that I used for this graph, which 2x squared plus 1, I believe. So that slope is 4, which should make sense because this one was 4.5, right, when we had the 2 points. And if we were to just consider the tangent line here, that's actually 4, so it's a little less steep. So that's what we've calculated. We've said if you were to graph that function and calculate the slope of the tangent line at that one specific point, in other words, the instantaneous rate of change at that point, x equals 1, is 4. So that is our derivative. That's your first derivative. All right, let's try another one. This one's going to be just a bit more complicated. I put the formula on there as well, but again, you do need to memorize this. So let's go ahead and try this out. We're going to find the derivative of this function, 3x cubed plus 2x minus 1 at x equals 2. So this is going to be f prime of 2, so a is 2, so a, equals the limit as h goes to 0. This is where it gets a bit complicated. It is going to be f of 2 plus h minus f of 2 over h. When we plug it in, we're going to have to plug it in a few spots. So this is going to become the limit as h goes to 0. This one's not the most fun one to do. There's a lot of operations you got to do, but it will work out if you do it right. It's going to be 3 times, and now we replace these x's with 2 plus h. So 3 times 2 plus h cubed plus 2 times 2 plus h minus 1. Okay, that's just the first part. That's the f of 2 plus h. We then have to minus f of 2. So f of 2 is going to be 3 times 2 cubed plus 2 times 2 minus 1. It's very easy to forget the constant, especially this constant here. It's very easy to forget that one. Don't forget it or else your function will not work. All right, just don't forget. All right, now we would want to try direct substitution. Can't do it because obviously we still got just an h in the denominator, so it's not going to work. So we're going to need to do some simplifying here. So let's just algebra our way through it. This 2 plus h cubed, maybe you want to just do that off on the side, the 2 plus h times 2 plus h times 2 plus h, just so it doesn't clog up your problem. Let's see, when we do this, we're going to end up with 4 plus 4h plus h squared times 2 plus h. So that's going to give us 8 plus 4h plus 8h plus 4h squared plus 2h squared plus h cubed. All right. Again, not the prettiest thing, but hopefully we did all that right. Just double check my math here. All right, looks good. Okay, so that's going to still need to multiply by 3. We can combine some like terms here. We've got 4h and 8h, which is 12h. 4h squared and 2h squared is 6h squared. So 8 plus 12h plus 6h squared plus h cubed. And I'm going to go ahead and just write those in order. There's going to be h cubed plus 6h squared plus 12h plus 8. And now you can see why you need algebra to do this. All right, and next we've got this term here. Let's go ahead and distribute that. So that's going to be plus 4 plus 2h minus 1. And then we've got minus this thing back here. 2 cubed is 8. 3 times 8 is 24. Plus 4 minus 1, so it'd be plus 3. So it's going to end up giving 27. All right, and then let's go ahead and do the next step. So then let's drop it down. Limit as h goes to 0. We need to distribute that 3 through. So that becomes 3h cubed plus 18h squared plus 36h plus 24 plus 4. And actually, I guess we could probably combine those. Oh, well. Plus 2h minus 1 minus 27 over h. And then let's just start combining like terms. And again, the goal here is to get rid of all the constants. Hopefully they all cancel each other out. If they do, that means we're in good shape. If not, then we made an error somewhere. So we've got 3h squared. We've got no other 3h cubed, no other ones. H squared, so we've just got that 18h squared. As far as h's, we've got 36 and 2, so that gives us 38 h's. All right. And then as far as constants, they should all cancel out. We've got 24 plus 4 is 28. And then minus 1 minus 27 is minus 28. So they do all cancel out. Don't assume they do. You need to double check, but that should be the case. All right, and this is over h. So we're in good shape because we got rid of all of our constants. We just have h's left, which means we can then factor out an h. Up here. So we've got the limit as h goes to 0 of, we're just going to again pull out an h. 3h squared plus 18h plus 38 all over h. The h's then cancel. Boom, boom. We're left with the limit as h goes to 0 of 3h squared plus 18h plus 38. We can then now plug in h because we've gotten rid of the denominator. So this becomes 3 times 0 squared plus 18 times 0 plus 38. 0, 0, 38 gives you 38. So that is the slope of the tangent line at 3x cubed plus 2x minus 1 at x equals 2. So that was pretty intense. Mostly it's just all algebra though. So there's not really anything crazy going on, just a bunch of algebra thrown in there. If you're wanting to know what this graph looks like, that's a pretty big number, but this graph looks like it's a pretty steep sloped cubic like that. So at 2, we're saying that the slope of this tangent line is 38. That's what we're saying. All right, so that is how you do it. Again, that is finding the derivative at a specific point. You might want to pause and stop there if you want to, and then go ahead and do the problems on this if you want. I'm going to go ahead and keep going and show you how to find just the general derivative. Okay, so in this next one, we're just going to compute the general derivative of 5x squared minus 2. We're not going to do it at a specific point, but what this allows you to do is compute a general derivative, and then you can actually just sort of plug in any point that you want to. So this is actually a probably better way to do it, but you need to know how to do both ways. All right, so we're going to use our basic just limit definition here. The only difference is we now just have x in there instead of a because we don't have a specific point. So the derivative of this function, f prime of x equals 5 times x plus h. And actually, well, I'll go a little bit slower here, sorry. F prime of x equals f of x plus h. We'll just write it out again. It's a good idea to write this out each time because it helps you get stuck in your brain. So our function here is 5x squared minus 2. So in the first time, the f of x plus h, we're just going to replace x with x plus h. That's all we're doing. Sort of the same thing we did in the last one. So then this becomes f prime of x equals, and I forgot my limit there, limit as h goes to 0. It is important to carry that with you every step. I know it gets a little tedious writing it, but if you can remember to write it for each step, that's a good thing. It's 5 times x plus h squared minus 2. So that's my f of x plus h. And then minus, parenthesis, just the original function, 5x squared minus 2 over h. So it looks very similar, except this time we've got x's mixed in there as well. All right, and then I'm just going to try to simplify this. We'll still end up with the same result as we did on the last one, except we're not going to have a single number. We're going to be left with a function at the end. So this is going to be the limit as h goes to 0. I need to square that x plus h. So it's going to become 5 times x squared plus 2xh plus h squared when we FOIL it out, minus 2. And then make sure this negative symbol gets distributed in there. Also, again, don't forget to write that minus 2, carry that down. It's easy to forget that. So then it's going to be minus 5x squared, and then plus 2 over h. And then we're left with the limit as h goes to 0. Just distribute this in. 5x squared plus 10xh plus 5h squared. And let's go ahead and cancel these. We got minus 2 and a plus 2, so no need to carry those anymore. Minus 5x squared over h. Now again, just like before, where we said we didn't want any constants left over, that's true. But in this case, we also don't want any just plain x's left over. Because if we have plain x's left over, we cannot factor out an h. And good news, that is the case here. You can see that 5x squared and minus 5x squared cancel. So we're left with then just the limit as h goes to 0 of 10xh plus 5h squared over h. So this is good because then we can factor out an h. And we're left with a 10x plus 5h over h. And again, when you pull out the greatest common factor there, you don't actually need to pull out the GCF. You can just pull out an h. I think it's actually more confusing if you would pull out a 5 as well, because then you got the 5 left over there. I think it's easier if you just do it this way, just pull out an h. So then they cancel. We are then left with just the limit as h goes to 0 of 10x plus 5h. So we can now go ahead and plug in our 0. So this becomes 10x plus 5 times 0. 5 times 0 is 0. So our answer then is 10x. That is our derivative. F prime of x equals 10x. That is our general derivative. You could say that the derivative of 5x squared minus 2 is 10x. Now what we could do then is we could find the derivative at a specific point. So let's say using this formula, f prime of x equals 10x, we wanted to find the derivative at x equals, let's say x equals 2. So at x equals 2, all we would need to do is plug it in. So f prime of 2 would then just be 10 times 2, so that would be 20. So the derivative, or the instantaneous rate of change of this function at this point, would then be 20. Or if I say, let's want to do f prime of 100. Well, I would just do 10 times 100, which would be 1,000. So the slope of the tangent line of this function, 5x squared minus 2, at the point x equals 100 would be 1,000. So this is a lot better, you would say, because it's more versatile, because you can then plug at any point that you want to. All right, let's go ahead and try the next one. All right, this one's just going to be a bit more work. So f prime of x, I'm going to go ahead and just, again, write out the limit definition. I've got it there, but I'm just going to go ahead and write it out. It's a good idea to do this, again, every single time. Limit as h goes to 0 of f of x plus h minus f of x over h. And then we're going to replace, we got to replace both x's with x plus h. Replace both of them. So what this is going to look like then is the limit as h goes to 0 of 4 times x plus h squared minus 9 times x plus h. So that's my f of x plus h. Then it's going to be minus parenthesis the original function f of x. So 4x squared minus 9x over h. And I got to do some work here to get this to where I want it. It's going to be the limit as h goes to 0. When we FOIL that first one, it's going to become 4 times x squared plus 2xh plus h squared. Distribute that through. It's going to become minus 9x minus 9h. And then we distribute this negative through to get minus 4x squared plus 9x over h. Okay, from there, again, keep in mind what I want to end up with is something on the top that all of the terms eventually have an h in them. When I distribute, we get 4x squared plus 8xh plus 4h squared. I'm going to go ahead and cancel out this minus 9x and a plus 9x. Those go away. Minus 9h minus 4x squared over h. Again, you do need to write out all these steps. If on the homework you don't write these steps out, I'm not going to give you full credit. So then we got limit as h goes to 0. We do get a 4x squared and a minus 4x squared. Those cancel. That's good because those are both x terms and they didn't have an h with them. So then what we're left with is an 8xh plus a 4h squared minus 9h over h. Now we can go ahead and factor it out. So limit as h goes to 0. Pull out the h, we're left with 8x plus 4h minus 9 over h. Cancel out our h's. Then we're left with the limit as h goes to 0 of 8x plus 4h minus 9. We now then are able to direct substitute. So that gives us 8x plus 4 times 0 minus 9. 4 times 0 is 0. So we're left with 8x minus 9. And that is our derivative, f prime of x. 8x minus 9. So this is, again, a formula we could use to find the slope of the tangent line at the point, whatever point we want of this function 4x squared minus 9x. So if we wanted to find the slope of the tangent line at x equals 2, we would then just plug in f prime of 2. So that would be 16 minus 9, which would be 7. So that would be the slope of the tangent line at x equals 2. So this is a very useful thing we've calculated, this derivative. We can use it to find this instantaneous rate of change or the slope at any given point on that function. Very, very useful. Again, this is a long way of getting the derivative. It's very important that you know how to do this, but there are shortcuts. And you might even be starting to realize in your mind, you can maybe start looking at the original function, look at this one, and see if you can start to make some connections on how we're going to calculate a derivative in future sections. I think we'll actually stop right there for right now. That's enough. We won't get to the really hard one. Yeah, it's a harder one, but we'll stop there for today and try your best on those problems. Reach out to me if you do have any questions.